Right, we're going to look at multiplication of fractions now, and the key is here in the red, top times top, bottom times bottom. I'll shrink that down a little bit to get it out of the way. We'll sort of line ourselves up. Right, we'll get going. So top times top is, so in this case, on the top line, 1 times 1, which is accepted as 1 on the bottom line. It's 4 now. Now, that may be the most simple of multiplications, but it's a good way of looking at it, because if I draw quickly a pizza and I shade in blue 1/2, and then I say, well, I'm getting a half of that half, then I effectively get this. Now, there's better drawn pizzas around, I acknowledge that, but so the half of a half we know is a quarter. We don't need the system, but it's good to see the system works on something we know. A good bit of language that comes out of that is, in this program I'm using the dot to stand for the times, but times can be replaced by, if you want a word, this simple little preposition, of. So half of a half is quarter. When I get a number times a fraction, then there's a couple of ways of remembering this, but essentially the whole number is just on the top line. So 5 times 1 is 5. The bottom line stays unchanged. You don't tamper with the bottom line. You can apply this other rule. You could, if you wanted, think of the 5 as a 5 over 1, and then the rule still works. The problem is, in books and actually on this program, it sort of offsets the whole number. So that it's half a line down. That's a bit of a mathematical convention, but that whole number is assumed to be on the top line. So 5 times 1 is 5. The 2 doesn't change. We think of the 2 as being establishing what kind of thing we're multiplying. If I go over here, there's a couple of different ways. We'll look at something on the next one, but I deal with the number separately. 3 5s are 15 on the top line. 2 2s are 4 on the bottom. That's accepted. I've got 1x on the top line, and I've got another x squared on the bottom. I can't simplify 15 over 4, there's nothing going on there, so it stays as it is. But that x knocks one of those out, just like in the last clip. So you're left with a 15 on the top and a 4x on the bottom. If I go to this one, drag, that's not worked out right. Here, again, the 6 is multiplied by the top line only, so 6 times 2 on a good day is 12x. And on the bottom line, the 5 doesn't change, or effectively gets times by 1. Now 12x over 5, whereas I had a bit of simplifying I could do last time, this time I haven't. Dive to the next slide though. When I've got several things multiplied together, and the key is that there's no plus or minus involved. Plus and minus are not going on here. This is about when everything says times are divided by together. I could go the long way and go 8 times 5 times 2, which is 80, and x squared y, so I suppose I could do that. But the problem is I've got something that I know I'm going to have to simplify. So what I can do before I start is I can say, well, 8 over 8, that gives me a 1, so I can ignore them. They cancel each other out. That 2 could cancel one of those 2's out, not both of them. And so I've done some simplifying. The other thing to say is, well, that x divided by itself, they cancel out. So now things are getting lean. Now I've got y squared here. There's nothing. Now I could take one of those and knock that out, because y divided by y. And now all I'm left with on the top line is 5y. And on the bottom line, all that hasn't been cancelled out is 2. Now, I could have done that the long way, and it would have worked the same. So 8 times 5 is 40, times 2 is 80, xy squared. On the bottom line, 2 times 2 is 4, times 8. 4 8s are 32. And I've got an xy. But I would have been stuck with having to cancel then anyway, and so that would have still knocked that out. That would have still knocked that out. And 80 over 32 simplifies to 5 over 2, because it's lots of 16. So better to use the top method. Okay.